they generated a calibration plot. And it's really a good idea to read over these calibration plots, because I remember Dr. Smith had one on his exam. A few students said that they didn't know what the concentration of the standard was. I believe that might be one of the questions. And in this one, we're measuring emission intensity versus our volume of standard that we're adding. And we also gave you the data from which this graph was derived from. And on the graph, it gives us our linear relationship between our y, our x value, 2.36, x plus 3.12. And that's our data. And the question is, a 25 milliliter sports drink, so we have a 25 milliliter sports drink that has sodium in it. It's very similar like we did our Gatorade example in 425 lab. It's prepared spiking a known concentration of the sodium chloride solution. So this is our standard. Our standard has a concentration 2.640 molar sodium chloride. Therefore, it's going to be 2.64 molar sodium ions in that standard that we're adding. And it's added to a total volume of 50 milliliters for each of these spikes that are listed in the data table. We have one that doesn't have any standard in it, and then we incrementally add 1 milliliter, 2 milliliter, 3 milliliter, and 4 milliliters of this standard. We measure our intensity, we generate our plot, and the question is, we want to calculate the molar concentration of sodium in that volume of sports drink. How do we solve it? What do you guys do in these types of problems? Remember? Well, we're given the standard concentration. We're going to extrapolate our data. What do we do to our data? We set y equal to 0. What we're going to assume is if we can calculate or determine where our 0 point is on y, that volume, the absolute value of it, we can multiply that by the standard's concentration, and that'll tell us the number of moles of sodium in that solution. If this is the volume, we're going to assume that when we extrapolate that data, the amount of sodium is from our unknowns, since that's the sample that didn't have any of our standard. If we know the number of moles of sodium, we know the volume, we can calculate the molar concentration. Seems reasonable. So if we set y equal to 0 and solve for x, x is just equal to negative 3.12 divided by 2.36. And remember, we're looking for the absolute value of that. That's equal to 1.322. And the volume of standard on this axis is in units of milliliters. It's not listed on here. I'll make sure I list it on the exam. It's in milliliters. That tells us that x value, when we extrapolate our data, is going to be 1.322 milliliters. If we know the concentration of our standard, we take the volume multiplied by the concentration, and that's going to equal the number of moles of sodium. And then we divide that by that volume. So what we'll do is we'll convert that to liters, to milliliters. Multiplied by the molar concentration. And that's going to tell us how many moles of sodium ion we have? We want to figure out the molar concentration. It equals the moles of sodium divided by the volume of the sample, and that should be in liters, 1.25 liters. That would be 0.1396 molar. Any questions? So that was number 11. So 12 we talked about a little bit in lecture. Let's go over 12 again. Isobaric interference is an interference that's typical for ICP mass spec. So 12, a review from what we did discuss, isobaric interference. This is the type of interference that we get in ICP mass spec. It's when we have a reactive or a molecular ion, perhaps like argon ion. Argon ions are isoelectronic with chlorine, therefore they're quite reactive. Oftentimes they're going to give us interferences in which these create molecular ions that have the same mass-to-charge ratio as our analyte. And we would measure that in the mass spec, and that would give us poor results. So we have to correct for that. If you remember from lecture, we said we can correct for it by adding a reactive gas into our collision cell. The gas that we used in our lecture was ammonia. NH3 was typical. NH3 is a reactive gas that we can either proton transfer to the ammonia or electron transfer from the ammonia to reduce the interferences from the molecular ions that are created by this argon ion. And that reduces that interfering species, and it helps to improve our results. Any questions on that? So that we talked a little bit about that in lecture. Another type of atomic measurement that we discussed in lecture was X-ray fluorescence. XRF, as you recall, X-rays are very short wavelength, very energetic particles. They give us a source of radiation, quite energetic. And one thing you should be able to do is when you're discussing resolution or instrument, if you're setting up an instrument, you should be able to convert from electron volts to nanometers in wavelengths. For example, let's convert 6.4 kilo electron volts to nanometers wavelengths. What we would need for this particular application is one of the equations I gave you on the equation sheet. So if you're looking at these problems on here, make sure you refer to the equation sheet. That's what's going to be given to you on these. A conversion factor here 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. So what we need to do is we need to convert electron volts or kilo electron volts to joules. Once we know that, we can use our Planck relationship to convert it to wavelength in nanometers. So the first step, let's convert 6.4 kilo electron volts to joules. .4 kilo electron volts is 6,400 electron volts. Our conversion factor, 1 electron volt that's going to be 1.026 times 10 to the negative 15 joules. Okay, now we have our energy in joules. We can use Planck's relationship. We're trying to convert it into wavelength in nanometers. Delta E, this is now our delta E value. That tells us a little bit about this energy. Is equal to H times C divided by wavelength. Wavelength is what we want in this expression. Wavelength is just equal to h, Planck's constant, times the speed of light, divided by the energy that we just measured or calculated. Planck's constant, again, it's given on the equation sheet. Speed of light, also given on the equation sheet. Divided by our energy. Yes? It's not on there? I didn't put it on there? I'll put it on there. Okay. Sorry, sometimes I take those for granted. Oh, everyone knows what the speed of light is. Some people don't. My friend knows it. She knows it miles per second. Okay. So I'll put the speed of light on. If I don't, I'll write it on the board for the exam. Okay, if we get our numbers, remember our answer is going to be in meters. There's the unit we're after. It's going to be in meters. We have to convert it into nanometers. So make sure you do your conversions on the exam. If we calculate our wavelength using all this data, we're going to get a data in meters 1.939 times 10 to the negative 10th meters, or 0.1939 nanometers. So that's how we would do that. Any questions on that? Well, I sort of put all these, topics in order, so we're still discussing X-ray fluorescence. And we went over some simple, I'm sure we went over a couple of review problems. Labeling XRF transitions. If we look at our not too bad. Let's put our letters in here, because what we're going to do is we want to understand a little bit about what kind of transition is occurring, and And we're going to use the older method of how they used to label these orbits. That would be called a K shell. The next shell is L. The next shell is M. And the shell there is N. And there probably is a few more. I think they take those up to K, L, M, N, O, perhaps. But these are the ones we're focusing on, some lighter elements. We're not going to get too heavy of an element. And the first transition that we're going to look at is one that's dropping from M to K. What will be the label for that? How will we label that? That's a K beta. Remember, the K represents where our hole is created at, or where we terminate, and it's beta because it's going through two energy levels of transition. So that is a K beta transition. Another one that we showed was one that started here and terminated on the L. That would be an L beta. Very similar. It terminates at the L level and it goes through two energy levels. So that's an L beta. So I think that's pretty explanatory. You should be able to do those without any problem. Any questions on it? '15 involves some instrument design for two types of diagrams. Make sure you can just draw a simple diagram. I'm not expecting anything to, I can't draw that a lot. I'm not expecting too much. In other words, don't spend a lot of time trying to make it look really good. You're not going to get extra points for really good looking diagrams. As long as you can explain to me what's happening in a simple block diagram and label things, that's what I'm at. Explain things. So we want to draw a wavelength dispersive XRF in simultaneous mode. And we want to list the advantages of it and compare it to the wavelength dispersive XRF in the sequential mode. So, wavelength dispersive. Now show me what you know what you're talking about. Let's make sure we understand what this instrument involves. There's two instruments. There's simultaneous and there's sequential. So first of all, what does the term simultaneous and sequential? This should trigger something in your mind. What's that, Amanda? Simultaneous measures all wavelengths at once. I agree. Sequential, well, it measures each wavelength sequentially. Okay, it's an XRF instrument. We need to have an X-ray source, obviously. Simultaneous. That's my X-ray source, nothing too extravagant. It's the box. We're shooting an X-ray in this direction. Okay, what does the X-ray hit for simultaneous? What does it go to first, the path? The sample. It goes to the sample. It's reflected off our sample. And it strikes. What's next? What kind of monochromator are we using? A crystal. We use a crystal monochromator here. Crystal monochromator. Now what happens is the energy, the X-rays that are reflected off of there are dispersed. when they're dispersed off the monochromator, we have individual detectors for each particular wavelength that we're interested in. That's why we can do it simultaneously. We have all these different detectors. The range, on a grid perhaps, detector 1, detector 2, detector 3. That's about as good as I would want you to draw. My lines aren't even pointing right at the detector, so I'm not going to be too serious with you guys on it. But I do want you to know there's an X-ray source. It goes to the sample first, then it goes off the crystal monochromator, and then it's dispersed on an angle at each of our detectors. And the reason why we do this is because we use Bragg's law to help us understand a little bit about how the crystal planes, and based upon the angle, how our X-ray goes into that, comes off, gives us the ability to scan different wavelengths all at one time. Okay? Well, then there's sequential. And sequential, the instrument's just set up a little bit differently. Again, it has an X-ray source. And unlike this arrangement, the source strikes the crystal first. Now what we do in this case is we rotate. We get a rotatable crystal. And that theta means we can change the angle of it. And then it strikes our sample. And there's only one detector now. Single detector because we change the wavelength based upon how we angle our crystal before it strikes our sample. Single detector. So you can probably see what some of the advantages and disadvantages of these are. This measures everything all at once. It's going to be faster. This will be good for batch analysis if you're working in an industry. This is a little bit slower. You might want to use this in an educational setting because you don't have a lot of money in education. This is more expensive, obviously, because we need more detectors for this particular arrangement. So that's the kind of thing I think you should be able to draw. You should be able to explain to me which one's faster, which one's more expensive, those types of things. They're the things that we're looking for when we think of figures and merit. Any questions? Another method that we discussed of imaging samples to tell us a little bit about a sample, how it looked, maybe some properties of its surface, was atomic force microscopy. Again, you should know your acronyms. I might just throw out, explain AFM. Draw me a diagram of a particular mode of AFM. If you don't know what AFM is, you're lost. AFM is atomic force microscopy. And this question, in which mode of AFM is the spatial variation of the cantilever deflection used directly to generate the topographic data because the height of the scanner is fixed? I think this one's kind of obvious. It's constant height. So let's think about atomic force microscopy. We have two modes that we introduced. There is contact mode and tapping mode. Contact mode, we discussed two different types of contact mode. There's constant force and there's constant height. So if we wanted to draw a picture of an AFM experiment and discuss either of these, or perhaps the tapping mode, we should remember what the instrument looks like. It involves a cantilever with a tip. And this is my picture of what a surface would look like. And this stage that the sample is on is a piezoelectric material, PZT material. And remember, we said a PZT material is a material that if we apply a force to it, it generates an electrical current, or if we apply an electrical current to it, it changes its shape. So it's kind of a unique surface. So what happens here, we have a laser that's directed off the back side of the cantilever, and it's reflected off the detector. It's situated in 4 quadrants. We sometimes call these quad cells. It's a position-sensitive detector that is sometimes also called a quad cell. And so let's think about constant force. Constant force, the cantilever is maintained in a certain position. It doesn't change. The sample stage itself is going to change as the cantilever tip remains constant on there, and the generation of this force on that surface is reflected in the PZT material that gives us an electrical current that helps us image it using some computer software. Constant height refers to the sample stage. It remains at a constant height. We move the tip across there, like I explained, vinyl and a record needle. The tip goes up and down. The tip's position is spotted on the position-sensitive detector, and they use that to help generate an image of the sample surface. So are you okay with that? That's basically all you need to know about that. Tapping mode. Well, tapping mode is a situation in which we use a certain frequency of how oftentimes that cantilever tip touches the surface, and we said that helps to understand a little bit about the nature of the surface, the adhesive properties of it. Is it hydrophobic? Is it hydrophilic? It tells us something about the type of interactions on it in terms of van der Waals forces or electrostatic type of forces. Another thing nice about tapping mode, it's less damaging to the sample surface itself. If we scratch it across there, I think I put some images on Blackboard, it does damage the sample and it might ruin the sample if we learn to use it for something else. Okay? Now, I briefly went over a little bit about micro cantilevers. I mean, this is just one small topic. It's an application of how we use, how I use atomic force cantilevers in sensing applications. So when we speak of MCs, these are micro cantilevers. Now what we do for micro cantilevers is we use them as sensing devices. We take an AFM, and we usually use the ones that are tipless, and what we do is we functionalize our cantilever. When we functionalize it, we put a surface on there that our analyte wants to bind to. That's basically what we're doing. We're going out fishing, analyte connects to our micro cantilever, and we have 2 modes that I discussed of how we measure. One measures changes in the micro cantilever's natural resonant frequency. These small devices, anything vibrates at a certain frequency. A diving board does, but it's so large we don't recognize it. And we get something at the micron level, we can actually measure that using some type of a computer or electrical program. What happens is, if we introduce an analyte on the surface that's specific for our analyte that it wants to bind to, well, that changes the mass of the cantilever, and that's going to cause changes in the resonant frequency. And we use that to help measure how much analyte's in a certain environment. So this is changes in resonant frequency. And this is called dynamic mode. Now, the way I used to think, because this is what we did in my research, my boss said, we're going to use dynamic mode or static mode. Dynamic mode, think about it, it's the resonant frequency. It's dynamically moving, and it's this change in the resonant frequency that we measure. So it's a change in the dynamic of the cantilever itself. So this is dynamic mode. Now, we can also use what's called static mode. That's actually the kind that we used when I was doing my research. And static mode is the optical method of watching or measuring the cantilever and how it bends or deflects. So this is the optical deflection method. So optical deflection. What happens is we have a micro cantilever, and we have it functionalized on one side. It's specific for our analyte. When the analyte binds to it, the cantilever might deflect upward or it might deflect downward. But what we have is we have a laser that's positioned on the end, and as the cantilever moves, that tells us a little bit something about how much analyte is in our sample. And we used quad cells too. We used these position sensitive detectors. We call those PSDs, PSD position sensitive detectors. So that's how we did it. Static mode, it's beam bending. Dynamic mode, changes in the resonant frequency. Any questions on that? That's about all you need to know on that. They actually talk about courses. Both of these methods, AFM and micro cantilevers, that's what grad course, that's the whole semester was all we talked about. It was pretty cool, actually. The guy that taught was excellent. He was like, really good guy. Not racist, really good. He actually was on the committee. Chapter 23. Chapter 23 dealt with an introduction to analytical separations. And we only got into one small section. So Dr. Desari will finish up the chapter. But I did get to talk a little bit about how we define our partition coefficient. K. As the concentration of our analyte and typically we're going to be focusing on the second phase as being the organic phase. And how it partitions out from the aqueous phase. And what we do in these types of situations is we do an extraction. We show how we take a funnel, a separatory funnel, we shake it up, and there's an extraction or a physical movement of our analyte from one phase into another based upon how it likes maybe an organic phase in comparison to an aqueous phase, like dissolves light. We also discussed a little bit about pH effects. Qualitatively, we discussed a little bit about acids and bases. we discussed acetic acid, and we thought about that one. If we have acetic acid and we want to separate it out of water, what would be a good pH? High pH or low pH, and why? Remember, we said based upon pH, we'll determine what kind of charge an acid or a base may have. Low pHs, acids are going to stay fully protonated. They're going to be more soluble in an organic solvent at a low pH. Higher pH, they get deprotonated, they lose their single proton, they get a negative charge. They're going to be more compatible with an aqueous solution or aqueous environment. Bases are the opposite. Low pH, they're going to pick up the proton, they're going to be charged, they're most likely going to want to go into the water phase. Higher pHs, they're going to remain neutral, they're going to want to stay in an organic environment. Make sense? So that's qualitative. We did some quantitative discussion on how we can do extraction. And this is question 18. Amanda, question?
No, I was explaining it to Brad.
Oh, you're explaining, Brad, you're okay.
Yeah, I was just like, you said solubility, right? Like it's more soluble in organic phase than low pH.
Well, it depends on if we're going to be an acid or a base.
Correct.
Okay, let's think about, let's just think about an acid. Let's just use a general acid. Since one person acid. Acids are HA, low pH. Low pH, there's a lot of protons in solution. It's going to stay in its fully acidic form. It's not going to lose its proton. It's going to be it's going to want to go into an organic phase because it's neutral. As we increase the pH, it's going to lose its proton and it's going to be charged. It's going to favor going into a water environment because polar water will be more soluble in the polar environment. Make sense? Bases are just the opposite. Okay? So this is low pH. This is high pH. Everybody comfortable with that? Very cool. Okay, question 18. Question 18 deals with how we conduct an extraction and how we understand a little bit about the efficiency of an extraction. So let's look at our question. In this problem, a solute has a partition coefficient of 4. Well, that's what our K value is. K is 4. And it's going to be extracted from 10 milliliters of phase 1 into phase 2. In this case, phase 1 is our aqueous solution. And what we want to do is do an extraction into the organic phase. K is 4. We're expecting our solute to be favored into the organic phase with a equilibrium constant greater than 1. Everybody okay? So we're going to look at two situations. A, we want to figure out what volume of phase 2 is required to extract 99% of the solute using just one extraction. So the first thing we want to do is define how our fractional amount in terms of the efficiency of the process. We gave an equation Q is equal to V1 divided by V1 plus K times V2. This defines the efficiency of the process. Q is going to tell us how much of our solute remains in the aqueous phase.
Are you going to put that on our equation sheet?
You got to know this one. You got to know this one. Okay. So A says, what volume is required to extract 99% of our solute? And it's the volume of phase 2. So let's think about what we're solving for in this problem. We want to figure out what volume of phase 2 is required to extract 99% of our solute. So first of all, V1 is the volume of our aqueous phase. In the first part of our problem, that's 10 milliliters. Everybody good? K is 4.0 that we gave you in the problem. Q. What's Q? Yeah. 0.01. And the reason is we're extracting 99% of it. Well, that means 1% remains left over in our aqueous phase. We want fraction. A fraction of 1% is 0.01. So everybody good with that? Q. Make sense? We've extracted 99%. 1% remains in the aqueous phase. If we convert 1% into a fraction, it's 1 divided by 100. It's 0.01. So now we just got to do some algebra now and solve for V2. If you do the algebra, I posted this. I posted the key. I went through the algebra. V2, if you do the algebra, got 10 divided by 0.01 minus 10 divided by 4. So if you separate and do your algebra, that's what you should be able. You should be able to break it down to that in your algebra. V2 that I got. $248. Okay. Part B. Part B, we're going to compare that efficiency with doing 3 extractions. So part B says, what is the total volume of solvent 2 needed to remove 99% of our solute if we do 3 extractions, 3 equal volume extractions? Everybody okay? We're going to use a very similar expression. And what we want to do in this case, we want to solve for V2 once again. Q raised to the 3rd power, this is equal to 0.01. Everybody okay with that? This value is going to be 0.01. Because we want to get the same 99% efficiency. V1 still 10 milliliters. K is still 4. And now we just got to do the algebra once again. I'll give you the answer right now. I'm not going to go through all the steps of the algebra. When I do the algebra, I got V2 is equal to 10 milliliters divided by the cube root of 0.01 minus 10 milliliters divided by 4. The volume I got for that one, I got 9.1 milliliters. So we can either use 248 milliliters in one plug, or we can use 9.1 milliliters in 3 plugs. Save some money on using our solvent. This one's more efficient than we need 3. Yeah, hey.
So the 9.1, we do it 3 times.
Right, so if we put that in here, and we do it 3 times, we should get 0.01 as our efficiency. That makes sense? Or we can do 248 in one plug. So if you do it 9.1 3 times, it's like 27, 28 milliliters total. Okay, you guys okay? Question 19 is a weak acid problem. We just discussed a little bit about qualitatively how we would solve a problem or think about a problem. 19 is a quantitative method for dealing with a weak acid. You okay, Delaney? Okay. A weak acid, we're going to consider the weak acid HA. And we're going to calculate the concentration that remains in an aqueous phase when 50 milliliters of the 0.0184, I'm sorry, 0.184. At a pH equal to 4.75 is extracted with 50 milliliters of toluene 3 times. We gave you the partition coefficient, K. K is equal to 5.17. And the Ka for the acid is 8 times 10 to the negative 4. Okay, how we solve it? You guys think we should do it? Okay. Well, think about what we want to do. We want to find out the concentration that remains in the aqueous phase. What we're looking for is the Q value, the efficiency of the process. Q, remember, just like we did before, Q is equal to the volume in the aqueous phase plus K times the volume in the organic phase. And we're doing it 3 times. This expression is good for single substances that only partition. They don't exist as more than one substance. Acids and bases, remember, they have charge species that we use the distribution coefficient place of the value for K. Acids and bases, we use D instead of K. We use the distribution coefficient because these substances exist in multiple charge states depending upon the environment that they're in. We said for acids and bases, we're going to assume that the charged species is only soluble in water. And we came up with expressions for D for acids and bases. These are on your equation sheet. You just have to know which one's the acid one and which one's the base one. So you just look over it and you'll have to remember it. So for an acid, the distribution coefficient D is equal to the partition coefficient K times the concentration of the hydrogen ion divided by the concentration of the hydrogen ion plus your Ka value. Now this is important, the distribution coefficient, because it tells us a little bit about how it distributes based upon pH and the strength of the acid, its Ka value. And it's also related to the partition coefficient, K. So we're going to use that in place of K in our efficiency equation. So we're given all the information to solve this. K is 5.17. Hydrogen ion concentration. Remember, pH tells us a little bit about H, our hydrogen ion concentration. The hydrogen ion concentration is 10 raised to the negative pH. And that's the same number here in the denominator. The Ka value we gave you in the problem, 8 times 10 to the negative fourth. And if we put all those in our calculator, we're going to get a value of our distribution coefficient of 0.112. Now remember, that distribution coefficient, it's analogous to the partition coefficient. It takes into account pH effects and the Ka of the acid, as we just discussed. We're going to use the distribution coefficient in our efficiency equation. The distribution coefficient is 0.112. Now this one, don't get confused. It's 50 milliliters of our aqueous phase, which is right here. And this is the volume phase 2, our organic phase. It's 50 milliliters also. I get 0.72725. That's the fraction that remains in the aqueous phase. And the question is, we want to calculate the concentration under these sets of conditions that remain in the aqueous phase. If this is the fraction that remains in the aqueous phase, and that's the initial concentration, all we do, fraction times the original concentration That tells us how much remains in the aqueous phase. I got 0.134 molar. Yes, ma'am.
The 7,272,000, is that just Q or is that Q?
That's Q cubed.
Okay.
That's this value right here cubed.
Okay.
That tells us what we get if we do those 3 extractions. Everybody okay with that? That's the study guide. Go over the suggested text exercises that I asked you. And I think these are very similar to some of the problems I